for today, we're just going to do the first half of this section. And so we're going to do just talking about how to solve exponential equations. Remember that when you solve equations, what you are doing is undoing operations because you're trying to get the variable isolated or by itself. And since in exponential equations, the reason it's an exponential equation is because the variable is the exponent, right? So in order to take care of that and to be able to solve for that exponent, we're going to have to be taking the log, because we talked about before in section 1 and 2 that an exponential function and a logarithmic function are inverses of each other. Go ahead. Now, the first type of exponential exponential equations that we're going to talk about are the very simple ones, where we can take the two sides of the equation and we can write it with like bases. If we can write it like bases, then we're going to use the theorem that says if b raised to the m is equal to b raised to the n, then m had to be equal to n. And we've used that idea already when we were evaluating some of our different exponents. So in checkpoint 1, they give us a couple here to do. Let's pull both of them up. And then part B. So like I say, this doesn't work for every exponential equation. It only works for these that have this particular form, the form where I can take both of these and write it to the same base. 125 is a power of 5, right? So I can rewrite this, and that's 5 to the 3x minus 6 is equal to 5 to the third, because 5 times 5 times 5 is 125. Since I can write it like this, this becomes a very simple product, a problem, because we're going to use this theorem that says if I have a like bases and they're raised to do two different exponents, the only way that can be true is if what? The exponents are equal. So I can take this equation and say, okay, this is a true statement if and only if 3x minus 6 is equal to 3. It's the only way it works, right? Same basis, so my exponents have to be the same for this to be a true statement. And now I can just solve this little simple linear equation. So I'm going to add 6 to both sides. So 3x is equal to 9. Divide by 3. X is equal to 3. And then you can go back in and you can double check. Plug it back in. 3 times 3 is 9. Minus 6 gives me 3. And 5 to the third is 125. Any questions? That's the second way I'm going to show you all how to do these. Okay, we've got two different classification of problems. We have this classification where we can make both sides be the same base, and then I'm going to show you the ones that can't. Only these special kind right here. There's not very many of them either. I'm just going to tell you right now. This is just a shortcut that only works for a very few problems. The other method I'm going to show you next works for everything. So even if you didn't notice that this was a one that you could do the shortcut on, it'll work with the other process. So you really don't have to remember this process. Sorry. Okay, so 8 is not a power of 4, right? Because 4 squared is 16. So obviously it can't be using 4 as my like base. What is my like base that I've got to be using? Not 8, because I can't take 8 and raise it to a power and get 4. We go smaller, y'all. We need a number that goes into both of these 2, right? So 8 is 2 to the third, and that 8 was raised to the x plus 2 power, so we got to write it that way. And 4 is 2 squared to the x minus 3. Now, we could have used those other numbers that you said, but then I'd have had fractional powers, and I don't want them. I don't like fractions. Okay? So I'm not going to say that what y'all were saying wouldn't work, because we could have made it work, but we don't want to have to use fractions. Okay, so if you'll go underneath and get a smaller number to find a number that raised to a certain power gives you the base, then that's a better deal. Now, if I have one exponent raised to a second exponent, what operation do I use? Multiplication. So I've got 3 times x plus 2 is equal to 2 times x minus 3. So 2 is my base, and the exponents on 2, I said equal to each other. And then I can do the distributive property, because now I'm just doing this nice linear equation that we've been doing since 8th grade, right? And solve this. It gives me 3x plus 6 is equal to 2x minus 6. Then we have to subtract 6 from both sides. So 3x, this is a 0 pair, it's gone. 2x minus 12. Then I've got to subtract the 2x from both sides. Here, this is a 0 pair, so it's gone. So I'm left with 1x is equal to negative 12. So x is equal to negative 12. And then you go back and plug it into the equation to see if it gives you a true statement. Okay? Like I said, this is a shortcut, and it only works for problems of this particular type. I don't know about that. But all right, so now we need to talk about objective 2 is being able to solve using just logarithms. Okay, so we're going to talk about how we can do this using logarithms, and this method works for any exponential equation. So if you happen to not notice that there's one that you can do the shortcut on, this method is going to work. Okay? So the steps for this is, first of all, you isolate or get by itself the exponential expression. So in other words, you don't want a coefficient, you don't want anything added to it, you want it by itself on one side of the equal sign. Then we're actually going to take the log, and we're going to either use base 10 or we're going to use the ln of both sides of the equation. Then we're going to simplify and solve for x. Okay, because what's going to happen when you take the ln is that you're going to be able to get rid of some stuff. Or take the log or the ln. It doesn't matter is what I'm saying. I usually do the ln of both sides because it's got 2 letters instead of 3. There is no reason to do one or the other. No advantage to do one or the other. Okay? So I just always do the ln. Left to right. That's right. Exactly. All right. So check point 2. So part A says 5 to the x is equal to 134. Part B, the second problem they want us to do there, is 10 to the x is equal to 8,000. Okay. So, first of all, do you see I've just got the base with the exponent by itself on the left-hand side there. So this is, number one's done for us. Step one is done. It's isolated by itself. Now, 5 is not an e and it's not a 10. So there's no advantage. So I'm just going to take the ln of both sides. Okay, so this is the ln of 5 to the x is equal to the ln of 134. Okay, everybody see it? The ln of both sides is all I did. Now, this is where I'm going to use that property that so many of you tried to use on the test in the wrong place. But this is one of the reasons why we learn how to use those properties before we start talking about this, because this is the ln of something raised to a power. So what can I do with that exponent? I can bring it to the front and multiply it so that it becomes x is equal to the ln of 5. X times the ln of 5 is equal to the ln of 134. Okay? So we use the properties to simplify, so I don't have anything raised to exponents anymore, so that's what that simplify means. Okay? Simplify using the properties. And then now I can solve it, because how do I solve this for x? Divide by the ln of 5 on both sides. So you get x is equal to, and then since I use the ln or the log, whichever one you wrote down, you can just type in using the buttons on the calculator. So just hit the ln. Don't forget that it's going to open a parentheses, and it's not going to do it right if you don't close that off after the 134 and after the 5. 3.04? Does it round to 3.04? Okay, good deal. Okay. It does say find the solution set and use a calculator to obtain a decimal approximation to 2 decimal places. So that's as far as we need to go. Okay? Any questions about how to do that? That's the process. Now, you need to be thinking. You don't need to just memorize this process and just regardless do the same thing every time. You need to be evaluating what's going on, analyzing the situation, and choosing the method that causes the least work. I know y'all just called me lazy a minute ago, but it's called working smarter, not harder, right? We've got to think about what we're doing beforehand. Now, when you look at this, what is the base? So would I use the ln? Would I take the ln of both sides? That's crazy. I can take the log of both sides, because what's going to happen on this one? Log base 10 of 10 does what? It just cancels out and it becomes 1 times x, which is just x, whatever the log of 8,000 is. And so instead of having to type in 2 logs, if you're paying attention, you can just type in 1 and be done with it. 3.9, it's 2 places past the decimal. 3.90, thank you. Any questions about how to do that? It doesn't, and if you'd used the ln on this, you hadn't noticed that the log of 10 would cancel each other out. You'd have had the ln of 8,000 divided by the ln of 10. And look and see what that gives you. Same answer. That's why I say it doesn't matter which one you do, but if you'll pay attention, you can knock a step out of it if you're paying attention. Right. 7 by 1. What is it? Did you make sure your parentheses are good? And did you, when you do the ln, you got to do the ln of 8,000 divided by the ln of 10, because you got to do the base. The base doesn't disappear on that one if you take the ln of it. DJ, what did you say about